Graphing Quadratics Part 1. This video will cover vertex form, so this is part 1 of 2. Before we jump into vertex form, for quadratics, the parent function is f of x equals x squared. Now we're going to take a look at the parent function and identify some key features of quadratics. Now I'm going to generate a table. In order to generate my table so that I get a full picture of what the quadratic looks like, let's analyze what the domain of our quadratic function is. So recall that the domain is all of the valid inputs that produce defined outputs. And when I look at x squared, there are no restrictions to that equation that would prevent me from getting some defined output. So the domain encompasses all real numbers. Now, because we have a domain of all real numbers, when I generate a table, I'm going to want to include negative values, positive values, and 0 to get the full picture. So let's choose some easy input values because we're doing this without the aid of a calculator. And when we evaluate the function at these points, we will get our corresponding y values. We'll get 4, 1, 0, 1, and 4. If we plot these points in our coordinate plane, connect them, because our domain is all real numbers, we will see that we get this very distinct shape, and that shape, that U shape, we refer to as a parabola. Now, as long as the domain is not restricted on our quadratic functions, we will always see this parabola shape. It might not be in that location or of that width, but it could be, or I should say, however, it will be in a different location depending on what transformation is applied. But just keep in mind that the general shape for our quadratics, as long as the domain remains unrestricted, will be this parabola shape. Now within that figure, we can also notice that there's a point that will be of interest to us. It's at 0, 0 currently, and this is what we refer to as the vertex of the parabola. So that vertex will be the highest or lowest point. In this case, the lowest. It will be the highest if that gets reflected over the x-axis. So vertex is at 0, 0 for our parent function. That vertex will move depending on what transformations are applied. So do not assume it's always located at 0, 0. Now something else that's interesting about the quadratic functions is that they have line symmetry. In the case of our parent function, we have mirror symmetry about the y-axis. And that line, that vertical dotted line that I just drew in, is what we call the axis of symmetry. And the equation for this line, because it's vertical, is going to be x equals some constant. In this case, it's going to be x equals 0. But this is, again, just for the parent function x squared. The actual equation for the axis of symmetry could vary depending on what transformations are applied. Now notice that it goes through the vertex. So identifying the axis of symmetry can be found if we identify the vertex because it will pass through that point. And the value of the axis of symmetry, or the equation for it, will correspond to the x-coordinate of our vertex. In the reciprocal nature of that, if I see the axis of symmetry, I know the x value for my vertex, which will allow me to find the corresponding y by evaluating the function at that point. So there are some key features. Now, how do we know the symmetry exists? Well, that symmetry looks like mirror image about the y-axis, which would imply that through a reflection, we are getting the same image. What type of reflection? Well, it's specifically over y, because if it was over x, it wouldn't look the same, right? So how can we confirm? If I apply a reflection over the y-axis, because it looks like a mirror imaging, my resulting equation will be negative x squared, and when I square that or simplify this, I get x squared. So what I originally had was x squared, and then through the application of the transformation, I still get x squared. So I know that a reflection over the y-axis or showing that mirror image about the y results in the same picture. So I know that symmetry is validated through that algebra. So that's another property that we want to utilize when graphing. Symmetry, the vertex, that parabola shape in nature, all of those things, if we can consider them, will be able to provide us with the information necessary to graph an accurate picture of whatever equation we are presented. But the equation types that we are going to focus on in this video are of the form that we refer to as vertex form. So vertex form is as follows. So vertex form is a times x minus h squared plus k. So looking at the parent function x squared, you'll notice the differences are these a, h, and k values. And these all represent constants. So don't think that these are variables. You will see them presented as numeric values. And we want to know what each one of these does to our parent function so that we can identify what types of transformations have happened, therefore where the new location of the vertex will be, where the parabola is wide, skinny, does it open up, does it open down, all of those things. So let's break down each piece and try to decipher what each represents. But first, let's look at what does A tell us? Well, A is some constant. It's being multiplied. So multiplication implies a dilation or a reflection. So in the case that A is something other than -1, we will have a dilation. So A, and specifically, it's going to be a vertical dilation because it's being applied to all of the function x squared. So we'll have a vertical dilation. Specifically, if A is greater than 1, that will give us a stretch. And if it's between 0 and 1, we'll have a compression. But what it can also tell us is that if A is less than 0, we can also get a reflection over the x-axis. Or sorry, yes. So if A is less than 0, then we will get, so let's add that in the bottom. So it tells us vertical dilation, and we'll say vertical reflection. And the vertical reflection will happen if A is less than 0, and again, that would imply over the x-axis. Because being less than 0 would mean that it got multiplied by -1. Okay? So that's what A will tell us. H. We see that addition subtraction to just x, in this case, is going to give us a horizontal translation. Now the general form of this vertex form shows -h. So if h is a positive number, then the general look will be x minus h squared, which implies that we're moving right. However, if h is negative, then subtracting a negative will reveal a positive, and the general form will look like x plus h squared, which shows us moving left. And then lastly, k. So adding k to the end will be a vertical translation. So adding k will move up, and subtracting k will move down. Now, some things that aren't revealed in this general form would be horizontal dilations or horizontal reflections, but I still need you to be able to identify them. So for example, if you saw something of that nature, where you have 1/2 times x within the parentheses, still be able to identify that horizontal dilation, or if instead we had a negative in there, still be able to identify that negative, indicating a horizontal reflection. So although it's not presented in that general format, you are still responsible for identifying those types of transformations. Now, what is the importance of identifying all of these? Well, through identification of translations, these translations will reveal the location of the vertex. So let's make a note of that. So translations move the vertex. So for instance, let's say we have we see that this goes right 4, down 1. Now the vertex starts at 0, 0 for the parent function, so if I go right 4, down 1, if I started at 0, 0, and I go right 4, down 1, well, I'm now at 4, negative 1. So there's the new location for my vertex. So using our knowledge of translations, we can identify the location of the vertex given vertex form. Now, because the transformations are so easily identifiable, we can make the conclusion that vertex form provides us an easy way to identify transformations, and that is why it is useful. So easy to identify transformations. We'll see another form in a different video where its use is slightly different. However, we still need to be able to identify these various aspects of the graph. Now, what you may be wondering is that why don't the vertical dilations have any effect on the location of the vertex? Why is it that just translations move the vertex if we could possibly have a vertical dilation? And the answer lies in how transformations are applied. So we are going to make a side note, which is of importance when reading off transformations when a function rule has been established. So let's look at the order of application for transformations. And this is when the function rule has already been established. So we are given an equation. Let's first look at vertical. The order in which vertical transformations are applied is dictated by the order of operations. An order of operations you may have come to know as PEMDAS. So what this means is that transformations that occur within parentheses happen before multiplication division, and multiplication and division transformations happen before addition subtraction, which means your dilations occur prior to your translations. And that is why the vertical dilation has no impact on the location of our vertex, because if we apply the dilation first, and it's currently at 0, 0, any sort of vertical dilation to the point 0, 0 remains at 0, 0. And then we can slide it left, right, up, or down to move the vertex. So vertical dilations have no impact on the location of the vertex because of the way the transformations are applied. Now horizontal follows the reverse order. That should be of no surprise, since everything is inverted with horizontal transformations to functions. So no, not common, we can just kind of reverse the SADMAP. Now also keep in mind that horizontal and vertical transformations have no impact on each other. So if there's both types within a function, it doesn't matter when you identify one before the other because they don't impact each other. So it's just a matter of if there are multiple vertical, multiple horizontal, identifying which ones occur first is important. And if you're still not understanding why, let's take an example with multiple vertical transformations. For instance, if I had a parabola, if I slide this up and then reflect it, so if I slide it up and then reflect over x so that it is at this final location here in green, that is different than if I were to reflect it first and then slide it up. So this final location is different from that final location based on the order in which those vertical transformations were applied. So knowing the order in which they're applied is important when it comes to being able to graph our function rules. So that is just a side note that we should be aware of. And the last thing for vertex form is let's make sure we can identify the location of that axis of symmetry. If we can identify the vertex through identifying horizontal and vertical translations and making that manipulation to the parent function location of 0, 0, also knowing that the axis of symmetry passes through the vertex, I'm going to be able to identify the equation for the axis of symmetry once I've identified where the vertex is. So the axis of symmetry passes through the vertex. So if the vertex is at HK, knowing that it passes through this point, and the equation for the axis of symmetry is x equals some constant, it must pass through the same x value on that x-axis as that vertex accounts for or relates to. So my axis of symmetry equation is going to be whatever the x-coordinate of my vertex is. So that is the conclusion to our first format for quadratics, vertex form. So looking at vertex form, be able to identify transformations, be able to locate the vertex, be able to locate the axis of symmetry, be able to identify, does this thing open up or down based on the reflection that has occurred, or whether or not if it has occurred. So keep in mind the vertex form, transformations easily identifiable, vertex form the vertex in vertex form is easily identifiable, hence the name. And the next video will cover the next format in part 2.